Today we're going to look at section 5.6. It does include parts of 5.5, but we're kind of combining it all into one. Our learning targets today to find possible roots of a polynomial with the rational root theorem. And we also want to be able to use the fundamental theorem of algebra to solve polynomial equations with complex solutions. So the first thing is this rational root theorem that says any possible rational root. And by rational, we're talking about things that can be written as a fraction. Okay, a fraction or a ratio. So things like 2, -1/2, 3/4, those kinds of answers we can find using the rational root theorem. It says that any possible one, so this theorem is going to give me all the possible ones. It doesn't mean they all work. They're the ones I can pick from. Okay, any possible rational root of a polynomial will be the factors of the constant term divided by the factors of the leading coefficient. Okay, so for this polynomial, 2x cubed minus x squared plus 2x plus 5 equals 0. The constant term is 5. So we would put factors of that constant term, so either plus minus, we could have factors of 5 being positive or -1, or positive and -5. Those become the numerator. And then the factors of the leading coefficient, which in this case is 2, factors of 2 are 1 and 2. Those would become our denominator. So what we're doing is we're looking at all the different combinations that have a 1 or a 5 for a numerator and a 1 or a 2 for a denominator. So possible rational roots for this particular polynomial would be these. Okay? So we take 1 and 5 and combine with 1 and 2 for our denominator. So we have 1 divided by 1, and it can be positive or negative, so we get positive and -1 as options. We can take 5 and divide it by 1, again, positive or negative. And then we can take our top numbers and divide by the 2. So we would have things like 1/2, again, positive or negative, and 5/2, positive or negative. So these are all the possible ones. And if I actually try them or I look at the calculator, I can see that I'm only finding this one that works. It gets me a 0. Okay? So we're going to go through kind of a 3-step process. Once we know these possible roots, we've made our list of options, we're then going to let the calculator kind of help us narrow it down a little bit rather than having to do what they've done here in the chart and evaluate at every single possible 0. Okay? So we will make this a little bit easier for you. So our first one here just says, what are the possible rational roots of these polynomials? So we need factors of 8. Factors of 8 would be 1 and 8, or 2 and 4. And factors of 3, which would just be 1 and 3. So my list of possible ones, again, these aren't all going to work, but these are the possible ones, are factors of 8, 1, 2, 4, or 8, over factors of 3. And again, it can be positive or negative, any of those options. So my list consists of positive and negative, 1 divided by 1, 2 divided by 1, 4 divided by 1, 8 divided by 1, 1 divided by 3, 2 divided by 3, 4 divided by 3, and 8 divided by 3. Okay? So I have plus minus 1, plus minus 2, plus minus 4, plus minus 8, plus minus 1/3, plus minus 2/3, plus minus 4/3, and plus minus 8/3. Those are a whole bunch of options. I certainly don't want to have to test every single one. So that's where that shortcut's going to come in a minute. All right, for this one, we need factors of this 10. So 1, 2, 5, and 10 are all the numbers that go into 10. And we're dividing by factors of 2, which would just be 1 and 2. So we want all of the pairs that have a 1, 2, 5, or a 10 on top as the numerator, and a 1 or a 2 for a denominator. So my list would be 1 over 1, 2 over 1, 5 over 1, 10 over 1, 1 over 2, 2 over 2, which is 1, and I already have that on my list, so I don't have to write it again. 5 over 2, and then 10 divided by 2 is 5, and we already have that on our list. Okay? So again, we have 1, 2, 3, 4, 5, 6 options positive and 6 negative. That means there's 12 possible numbers that I could try to find a 0. Okay? The fundamental theorem of algebra says that if p of x is a polynomial of degree n greater than or equal to 1, then p of x equals 0 has exactly n roots if you include all multiples and complex or imaginary roots. Okay? We've been talking about that. The degree tells me how many zeros I should be finding. So in this first example, we have an x squared, and you can see that there's 2 places where it hits the x-axis. There are 2 real zeros. I can see them. They are real. In our second picture, it's still an x squared graph, but this time it only has 1 real 0. But because of that shape, it's touching and bouncing off the x-axis there, we know that that has a multiplicity of 2. So it does count as 2 zeros. In the third example, again, we're still looking at an x squared graph, but it doesn't touch the x-axis at all. So we have no real zeros, but it has to have 2. So that means we must have 2 imaginary, since we're not seeing any places on the x-axis that it's crossing. All right, so how do we put this all together? To find all of the roots, and notice it says all, real, imaginary, everything. We're going to use the fundamental theorem of algebra to tell us how many roots we're looking for, okay, based on that degree. Okay, what is the degree of your polynomial? That's going to tell you how many zeros you're looking for. We are going to make our list and use our calculator to help identify some rational roots that we could try. And then we're going to synthetically divide out those roots to check. Okay? If the polynomial you have left is now a quadratic, we can always solve either factoring, square rooting, quadratic formula. We have options. So the idea here is to take a higher powered polynomial and get it down to something that we know how to solve. Okay? So, by the fundamental theorem of algebra, we are looking for 3 roots since we have an x to the third. Okay? So, our next steps, we're actually going to go through really a 4-step process if you count this first one. We're going to make our list. Then we're going to look at our graphing calculator. So I'm abbreviating graph suggests. Okay? And then our third step is we do have to prove these algebraically. All right, so looking at this, we need factors of 6, 1, 2, 3, or 6, divided by factors of 1, which would just be 1. So my list consists of 1 over 1, 2 over 1, 3 over 1, 6 over 1, and it can be positive or negative. Okay? Then my graph suggests means I have to go to that calculator and figure out, well, which of these numbers, there's 8 of them, 1, 2, 3, 6, and they're negatives. There's 8 possible ones. What am I looking for? Okay? So we're going to go to our calculator, and we're going to type our equation in. We have y equals x to the third minus x squared plus 6x and minus 6. Okay? We're going to graph that. I'm just going to do a zoom 6. It gives me a nice graph. And it looks like it's crossing at a 1. Okay? I'm looking for where it's intersecting that x-axis. So my graph is suggesting that 1 is a real 0. Okay? So then I go back. I'm going to list that. My graph suggests that 1 works. Okay? And now we're going to go through the prove step. We have to use synthetic division to show that that actually works. Okay? So we want to prove that 1 gets us a 0 remainder. Okay, it's truly a 0. My coefficients are 1, -1, 6, and -6. Okay, using that synthetic process that we've learned, we bring down our first term, multiply. 1 times 1 is 1, and we add. Then we multiply. 1 times 0 is 0, and we add. 1 times 6 is 6, and we add, and we do get a 0. So we've proved that 1 is a 0. But remember, we're supposed to have 3, so there's 2 more out there that we're not seeing. Looking at what we have left, we have no remainder. This is my constant x squared. So I have x squared plus 6. And I have to figure out now what are the zeros from that. So if I subtract my 6 to the other side, and then I square root, you can see that we are getting imaginary answers. So this tells me that x could equal positive or negative I root 6. So those are my other 2 zeros. So I do have 3 of them, a 1, a positive I root 6, and a negative I root 6. All right, our next example. It says use the fundamental theorem of algebra to find the zeros of x cubed plus 2x squared minus 13x minus 26 equaling 0. So again, that first step says if we have degree 3, we are looking for 3 roots. All right. We need to make our list. We need to look at what our graph is suggesting as possible zeros, and then we need to prove them synthetically. Okay? So factors of 26 over factors of 1. It's always nice when your leading coefficient is 1, then our denominator is just a 1. The factors of 26 are 1 and 26, or 2 and 13. And again, we're dividing them all by 1, which doesn't do anything. Okay, let's go to our calculator and see what this graph shows us. So we are going to put in x cubed plus 2x squared. And you can do second delete, that's an insert. So I can put a 2 in and it just bumps everything else over. Then I need minus 13. Minus 13x minus 26. Okay, we're going to look at our graph again. Now remember that we had factors of 13 and 26, and I'm only going out here to 10. So I do have to keep that in mind. I might have to make my window bigger. But we said there were supposed to be 3 zeros, and I'm seeing 3. So they are all real numbers, but this is the only one that's hitting at either 1, 2, 13, or 26. Those are my only options. So it looks like I'm getting one at -2. And then these, because they are fractions or decimals, and I didn't have any of those on my possible list, I'm not going to deal with those right now. I'm just going to start with that -2. Okay, so I'm going to say my graph suggests the -2 should work. So let's prove that. We have 1, 2, -13, and -26. We bring down our 1 and multiply. Then we put it in our next column and add our columns. Again, we multiply. -2 times 0 is 0, and we add. Multiplying -2 times -13 is 26, and we add. And so we have proved, because we have a remainder of 0, that -2 is a 0 of my polynomial. Okay? But let's look at what we have left. It's important to analyze that because we still have 2 more zeros to find. So let's focus on this piece. We have an x squared, no x's, and a -13 as our constant. And we need to find zeros of that. So we're going to add the 13 to the other side. We're going to square root. So we end up with x equaling positive or negative the square root of 13. Now, let's grab our calculator and see what is the square root of 13. So if I do square root of 13, I'm getting about 3.6. And we said we had positive and negative square root of 13. So again, if we look at our graph, we're looking at a 3.6 here and a negative 3.6 there. Those are the other two real zeros. They're just not rational ones. And my list only contains the ones that are rational, that can be written as a fraction. So the zeros that I have found, negative 2, positive root 13, and negative root 13. And you can write that as plus minus root 13 if you want. All right. Let's try one more. Our polynomial is x cubed minus 2x squared minus x minus 6. Again, we are looking for 3 roots because of that. All right. So let's make our list. We need factors of 6 divided by factors of 1. So my factors of 6 are 1, 2, 3, and 6. Factors of 1 are just 1. So I just have the numbers 1, 2, 3, 6, negative 1, negative 2, negative 3, negative 6. All right, we need to graph our equation and see if any of those appear. All right, so our equation, pull it up here again. We had an x cubed minus a 2x squared minus an x and minus a 6. Okay, so there's my new equation. I'm going to look at the graph. And this time it looks like it's only touching right here at 3. But 3 was on my list, so that's fine. I can try 3. So my graph is suggesting that 3 works, so let's prove it. We have coefficients of 1, negative 2, negative 1, and negative 6. Again, I'm just taking them from my polynomial. Bring down our first term and multiply. 3 times 1 is 3. Adding, we get a 1. Again, 3 times 1 is 3. Adding, we get 2. 3 times 2 is 6. Adding, we get 0. And since we have a 0, we know that that is a true x-intercept or 0 of my graph. So my zeros, I have 1 at 3. And remember, we have 3 of them defined, and so we're still missing 2. So let's look at our polynomial that we have left. We have a constant, an x, and an x squared. So x squared plus x plus 2. We need to find the zeros of that. It is quadratic, so we can go through our quadratic formula. X equals the opposite of b. Our b was 1, so we need negative 1. Plus minus the square root, b squared. So 1 squared minus 4 times a times c, all divided by 2 times a. So we get negative 1 plus minus the square root of stuff all over a 2. Inside our square root, we have 1 squared, which is 1. We're subtracting 4 times 1 times 2, so we're subtracting 8. So we have negative 1 plus minus the square root of negative 7 all over 2. Because that's a square root of a negative, that's imaginary. And that's why we did not see them on our calculator. We only saw the real one at 3. So my zeros would be a 3 and the 2 imaginary ones. Negative 1 plus minus I root 7, all divided by 2. Okay? So we're going to have you practice that 3-step process. Make your list, graph them on the calculator, and try to narrow down that list, see which of those options work, and prove those. And then once you've proven the ones you saw on the calculator, you can use your polynomial that you have left over to solve and find the rest of them.